We haven't been to the stars. We may never get to the stars. We can't smell the stars, we can't hear the stars, we can't touch the stars, and therefore, the only thing we have to study the stars by is the light they emit.
What astronomers have done over the years is gotten more and more subtle in their analysis of light. The key thing people want now when you want to have a new astronomical object is the spectrum. The spectrum, the pattern of frequencies of light coming off of a star or off of anything, tell you so many things about it. They tell you the temperature, they tell you what it's made of. By subtle analysis, you can find the size, the pressure, you can find how fast it's moving. All this coming just from measuring in detail the light.
To uncover the hidden messages in this celestial light, astronomers must divide it into its component wavelengths. Colorful patterns of light that reveal the secrets of the stars. The scientific study of the components of light began with Isaac Newton's experiments in optics during the late 17th century.
Sir Isaac Newton passed white light from the sun through a triangular piece of glass called the prism. As a result of that, he observed a continuous spectrum of light, the rainbow of colors ranging from the violet to the red. In the early 1800s, Joseph Fraunhofer conducted the same experiment that Sir Isaac Newton did with the light of the sun. Only this time he used a very powerful magnifier to look at the spectrum in more detail. As a result, he discovered that the spectrum was filled with a bunch of dark lines.
Just put sunlight through a good spectrum analyzer and looked at the different colors that were there, and he said, look, there's all these gaps. What do they mean? He didn't really know. Fraunhofer then later was basically cataloging all the different kinds of spectrum that he could find and kind of naming all the different lines.
The significance of these dark spectral lines remained a mystery for half a century. Then, two German chemists lit upon the answer.
It was a wonderful discovery made in Heidelberg in 1859 by Bunsen. His name is famous for anybody who's taken chemistry, for the Bunsen burner, and his protege, Kirchhoff.
Chemists had observed that if you place chemicals, elements inside of a burning flame, they would produce a variety of colors, a color particular to that kind of chemical. In particular, they would place the light coming from these flames through a spectrograph. To their surprise, Kirchhoff and Bunsen discovered that these flames produced a pattern of very bright lines. They continued the examination of these various flames and discovered that each of these patterns were unique.
One day they looked out the window or across the Rhine plain to the distant town of Mannheim, and it seems something big was on fire there. And they remarked to each other, you know, if we had our spectroscope here, we could find out what Mannheim is made of. And then it occurred to them that, well, they could use this same technique to look at the stars and find out what the stars were made of. One thing led to another, and that was the key for unlocking the chemistry of stars.
It wasn't too long after that that Kirchhoff and Bunsen began to examine the lines Fraunhofer had cataloged. And to either their surprise or their satisfaction, they discovered that the dark lines that Fraunhofer had discovered fit exactly in the same positions that the bright lines they had discovered in their laboratory. The conclusion was that the dark lines coming from the light produced by the sun were produced by elements that Kirchhoff and von Bunsen had examined in their laboratory, hence the birth of astrophysics.
Through a series of trial and error experiments, Gustav Kirchhoff later identified the conditions necessary to produce 3 different types of spectra: the continuous spectrum, the emission or bright line spectrum, and the absorption or dark line spectrum.
The continuous spectrum occurs when you take a solid material and heat it to the point of glowing, such as the filament of a light bulb, incandescent light source. Continuous spectrum are also produced by taking a liquid or a gas under very high pressure and making it glow.
You take white light and you put it through a prism, like from a light bulb, and you'll see red, orange, yellow, blue, indigo, violet, the whole rainbow there, and there's no break or gap. Every wavelength is represented.
A bright line spectrum, which Kirchhoff observed directly in his laboratory, is produced when you get a thin or rarefied gas to glow. An astronomical source that would produce a bright line or an emission spectrum would be what we call an emission nebula, the Orion Nebula as an example, or the Lagoon Nebula. They produce an emission spectrum or bright line spectrum because, in essence, the Orion and the Lagoon nebulas are hot, rarefied gases that are glowing. The reason they're glowing is because there are stars embedded within them, causing them to glow.
When the gas involved is less dense, then you may get an emission spectrum. You get just the lines. These are very important because they can give you the chemical elements that are in that diffuse gas.
The dark line spectrum, which Fraunhofer observed coming from the sun, in fact, what we observe when we look at spectra from the stars, is a combination, sort of a combination of the two. From deep within the star, we get the continuous spectrum. And yet that light produced by that very hot source must come through a cooler atmosphere. So that hot light passing through that cooler atmosphere causes that atmosphere to literally subtract or remove those spectral lines unique to the atoms within that cooler atmosphere. And we get the dark line spectrum, or sometimes called an absorption spectrum.
So, a hot, dense object produces a continuous spectrum. A heated, low-density gas produces a bright line spectrum. And a hot, dense object, such as the sun's interior, seen through a cooler gas, such as its atmosphere, produces a dark line spectrum unique to the elements in that gas. Even though early physicists knew this was how light behaved, they did not know why. For that answer, they would first have to discover how light interacts with nature's smallest particles.
In order to know what light is and how it's produced, we need to understand the atom. When we understand the atom, we can understand how stellar spectra are produced. We understand the light from the stars, and with that information, we can understand the stars themselves.
We know nowadays that atoms are made of protons, neutrons, and electrons. That's the 3 main subatomic particles. The protons and neutrons stick together in the nucleus, which is a very small place compared to the size of the whole atom. The proton is plus charged, the neutron is neutral. The electron, 1 electron per proton, electrons form a large cloud all the way around it, and because opposites attract, they're negatively charged. The electrons try to get as close as they can to the nucleus.
We're faced with the problem that if this is the way atoms were, and electrons moved in around the nucleus without a definite orbit, and they'd spiral into the center, then the universe would be over shortly after it began. Niels Bohr created what referred to as stationary orbits. These orbits are now referred to as energy levels.
It's, in a sense, energetically like a soccer ball on a step of stairs. The soccer ball wants to be at the bottom of the stairs gravitationally, and that's the electron being as close as it can to the protons in the center. That's the ground state, and then, but you could put a soccer ball up 1 level, and that's the next level orbital. So there's all these different orbitals, and they have different energies, but each atom has a very different set of stairs. And there are thousands of stairs. So it's a very complicated set of energy levels that describes each atom uniquely, like a fingerprint.
Electrons exist in an orbit or energy level around the atom. Under normal circumstances, these electrons remain in their lowest energy state, the ground state. If those electrons are stimulated by some form of energy, could be visible light, could be heat energy, it can be ultraviolet energy, whatever the case may be, these electrons become excited.
One way is to have some other atom come and bump that electron up into the next level. Okay, that's one way. Another way is if a photon of just the right energy comes along, that electron can absorb that energy, kind of just take that photon out of existence, and it goes up to the next level, having basically eaten that energy.
That transition lasts for maybe a millionth to a billionth of a second. The electron then will make another transition back down from a higher energy level to a lower energy level. When that occurs, the electron must release the amount of energy it had acquired to make the transition upward. When it makes the transition downward, emits this amount of energy, this photon of energy, a spectral line is produced.
Now this is very interesting actually, because suppose a photon of the wrong energy comes along. Suppose it's sitting here on the ground state and it wants to go to the first excited level, and a photon comes along that doesn't have enough energy to lift it up. Well, then it can't absorb that. It could try, but it just wouldn't go anywhere. So that photon can then just go right through. It won't get absorbed, and the atom will sit there in its ground state. Suppose a photon comes along that has too much energy that actually would make it go between, say, not to the first excited state, but somewhere in between. That photon will also just pass through because it would leave the thing in a wrong spot. So it's only certain photons that can actually be absorbed. Of course, once it's in the first excited state, it could then receive another photon to move it to the third or the fourth excited state.
Depending on the level of the transition, how far that electron jumps from a higher energy level down to a lower energy level, that electron may emit visible light, may emit ultraviolet light, infrared light, X-ray energy. It all depends. But whatever is emitted, the energy emitted is unique to the atom and hence the element.
This is the clue for discovering what atom is there, or one way of finding out, because each atom has a unique set of energy levels, so it has a unique set of photons that it can absorb, a unique set of wavelengths that it can absorb. So each transition between different levels gives out a photon of a very peculiar wavelength. This is what allows us to actually look at atoms making these transitions. We don't see the atoms, we don't see the electrons, we see the photons.
And that is why when we get billions and trillions of atoms becoming excited and electrons making transitions, we see these spectral lines continuously observing or identifying the elements that make up the gases that are glowing.
The objects that glow in the night sky send us distinctive patterns of spectral lines, clues from which astronomers uncover the secrets of the stars.
Spectroscopy has played a critical role in the development of modern astronomy because it really ushered in the modern era of astrophysics. Spectroscopy allows you to understand the physics of objects.
If we take a clear gas in a glass tube and attach electrodes to the ends and run an electrical current, we can stimulate that gas to the point of glowing. By analyzing the light coming from this gas tube through a diffraction grating, we would see spectral lines which identifies that element. If we look at other gases through a diffraction grating, we see the spectral lines of that gas. These spectral lines are unique to that gas. They are fingerprints which enable us to identify that gas even when mixed with all others.
That is, a person who studies spectra can look at the pattern of emission lines, that is, at what colors the light is coming out, the photons are being created, and thereby identify what kind of atom it was that must have made the light.
So when people started looking at stars, they immediately said, I recognize this set of lines. It's like recognizing the face of a friend. That is hydrogen. That is neon. And so people were able then to be able to tell in the sun and in the stars, places that they had never dreamed that they could visit. Suddenly they were given a tool that will allow them to see all the different chemical elements.
Astronomers can determine the chemical composition of stars using a spectrograph, like one of those here at the Kitt Peak National Observatory in Arizona.
We are now inside the KOCE spectrograph of the 2.1 meter telescope. The light comes to a focus just outside this room at a place up there. The light is converging from the telescope, comes to a focus, and there you see a very small star image. Once it goes through the entrance of the spectrograph, it diverges, and from that place it hits the mirror down at the lower end, down there, called a collimating mirror, and that makes a parallel beam of light, which then comes up and hits this grating. This is the essence of a spectrograph. This is where the white light is broken up into a spectrum of colors. This is a camera here that we use to take a picture of the spectrum. Now let me go down and point out some things about the detector. The detector is a CCD chip, and that chip is inside this container which contains liquid nitrogen. This chip then will produce a picture of the spectrum by building up an electrical charge on each of the 1 million pixels. So that is how we take a picture without a photographic plate of a spectrum of a star.
Now there are other new kinds of instruments as well. For example, using fiber optics, in which you can actually send light down a fiber tube that can be bent. Now, using fiber optics, you can build what's called a multi-object spectrograph, in which, for example, you have a field of view, let's say, with 100 stars in it. And rather than going one star at a time and taking the spectrum of each one separately, each one of these stars is connected by a light pipe to the slit of a spectrograph, and you can then photograph the spectrum of all 100 stars simultaneously. And obviously, you're gaining a factor of 100 in a given exposure time.
At Palomar Observatory near San Diego, California, astronomers have made a stellar leap in gathering spectra by applying fiber optic technology to the 200-inch Hale telescope.
The instrument that we built here has the ability to observe up to 176 objects at a single time, thus improving the observational productivity of the telescope. So we have in fact created 200 Hale telescopes by the production of one instrument. Before we come to the telescope, we have decided the objects we're going to observe, and we have somehow determined positions of all the objects within this field. Through a series of programs, we determine particular positions of the fiber optics, how we're going to place them on the stage. And we have a robotic system which picks up each fiber and places it onto the focal plane of the telescope in the position that we think the object will be at. In order to determine what wavelengths that we are covering, we have to take comparison spectra. And down over here we have a panel which allows us to take comparison spectra of various gases like argon, helium, neons, and mercury. This particular monitor shows the data that we've actually collected. Now we'll plot the spectrum of a star we got last night.
This multitude of lines is literally the spectrum of many, many gases. And yet, when we compare a laboratory spectrum with the stellar spectrum, we can isolate and pinpoint every single element that we can find a match to. We can know the chemical composition of the star.
The first star, of course, that we knew anything about the chemical composition of was the Sun. The Sun is our nearest star and the one that we can analyze with great precision. As telescopes and techniques became more sophisticated, it was possible to interpret the chemical composition of nearby stars, and it was found that almost all of the nearby stars have abundances very much like the Sun. In fact, you might call them sort of a standard chemical abundance with a high percentage of hydrogen, some helium, and a smattering of heavy elements.
While nature forged the stars from the same basic elements, their spectra appear to be different. It turns out these differences reveal much more than chemical composition.
When astronomers first started observing the spectra of stars, they found that there were great differences from one star to the next. And the initial assumption was that those differences were caused by differences in chemical compositions. There were some stars in which they would see strong lines of helium, others in which they would see strong lines of iron. And so the initial idea was that perhaps the helium stars were rich in helium and the iron stars were rich in iron. Turns out that's not right.
If you compare the stellar spectra of one star with another, just line them up, you discover very quickly that some of those lines are very thin, some of the lines are much broader, much more intense. The reason for the difference in intensity or strength of the spectral lines turns out that it has to do with temperature. It's the strength of these spectral lines that enable us to determine the temperature of the stars.
In a very hot star, there is enough energy present to ionize most elements, that is, to remove the electrons completely away from the atom. That means you can no longer form spectral lines because the electrons are missing. And so you tend not to see any iron, or even the hydrogen lines are quite weak in very hot stars. If we go to very cold stars, there are certain elements like helium where it takes an enormous amount of energy to produce a particular transition, a particular absorption line. And there simply isn't enough energy in those stars. Those stars are too cold to produce helium lines. On the other hand, it's rather easy to produce energetically. It doesn't take very much energy at all to produce an iron line, and so you can get iron lines in cold stars.
The relationship between the surface temperature of a star and its spectrum provides astronomers a convenient way to classify and distinguish between stars.
The original classification scheme, like any classification scheme, was designed to go from the simple to the more complex. And so when Annie Cannon, a pioneer in this field at Harvard College Observatory, started her work on spectral classification, she and her collaborators put the simplest spectra into class A and the more complex ones as class B, and so on down the alphabet.
When we understood that these strengths of the spectral lines corresponded to temperatures in the atmospheres, most of the letters were dropped. They were slightly rearranged, those that remained, now according to their temperatures.
And so the hottest stars we now know are the ones that were called O stars in this early sorting process. And the next hottest are B stars and A stars, and so forth down the spectral sequence. And so that's why it's a peculiar order, O, B, A, F, G, K, M. Or, in order to remember it, astronomers for a long time have said, oh, be a fine girl, or guy, kiss me. And that's how we remember the order.
Each of those spectral types corresponds to a temperature ranging from about 50,000 Kelvin all the way down to about 2,000 or 3,000 Kelvin. And in fact, our sun is spectral class G2. That spectral type corresponds to a temperature of 5,800 Kelvin.
In addition to revealing a star's composition and temperature, stellar spectra offer clues about the motion of stars.
In the last century, it was discovered that the wavelength of light could be changed, or would be changed, if the object emitting the light was moving toward the observer or away from the observer. And this has become known as the Doppler effect for one of the earlier studiers of this effect. We can also hear it in sound. The pitch of sound depends on whether something is approaching us or receding from us.
The Doppler effect also applies to stars and starlight. If a star is approaching us, then the light coming from that star will be slightly shifted towards the blue end of the visible spectrum. And so if we can compare a laboratory spectrum with the stellar spectrum, we would discover the line slightly shifted. The amount of shift is directly related to the speed at which the star is approaching us. On the other hand, if the star is receding away from us, then the shift of those spectral lines will be slightly towards the red end of the spectrum. We would say it's a red shift.
It's pretty incredible. 100 light years away, there's a star. You can barely see it. It's dim. But you can measure by looking at the shift of these lines exactly how fast it's moving.
We can also determine how fast a star is rotating. Imagine a star that is spinning around its axis this way. As this side rotates towards you, those lines will be, on that side of the star will be Doppler shifted to the blue. On this side, which is moving away from you, those lines will be Doppler shifted to the red. That makes the whole absorption line much broader than it otherwise would be. And so from the width of the line, we can tell how fast a star is rotating.
So the Doppler shift is used throughout astronomy, even to measure the speeds of galaxies halfway across the universe, which move at substantial fractions of the speed of light.
For over a century, astronomers have used spectroscopy to unravel the mystery of the stars. Even today, we continue to probe the universe by collecting starlight and analyzing spectra.
As time has gone on, the spectrograph has gone from a visual instrument through which astronomers looked to a photographic instrument which could record light. This allowed astronomers to take spectra of ever fainter objects, of more stars, to measure Doppler shifts, and to do quite a number of things that could not be done in any other way.
Now what we are doing is using that information to try to understand how our own galaxy evolved. When did the stars form? Where did they form? And so we're using what we understand about individual stars now to understand how the whole system of stars that is our galaxy evolved.
For the first time, we have some hope of getting spectra of galaxies at near the time of their formation. That is, we can look to such large distances, which is equivalent to looking back in time, that we hope that we can actually get the spectra of forming galaxies. Taking a picture of them may be interesting, may show you something, but it's usually the spectrum that's required to understand what is really happening there.
While the stars themselves exceed our reach, their spectra put an understanding of them within our grasp. Decoding this light from above continues to provide our most powerful means for unlocking the secrets of the infinite frontier.